Hello everybody, and we are continuing on with light. We're at 7.3, Scattering and Dispersion. If you haven't read Coletta, chapter 23, please do so. We're going to be moving on to chapter 24, which is spherical mirrors and lenses pretty soon, so we've got to get ready for that. So let's go ahead and get started. So if you ever looked up we've all looked up at the noonday sun, and you've kind of seen the blue sky and wondered why is that. And typically, if you ask somebody, you just get a response that's scattering of light and doesn't really move past that too much, right? But we're going to get into what is the scattering of light right now, so that we all have a better understanding of what is going on and how is light actually scattered, right? If light is carried by a photon, which is a massless, chargeless object, how can something that has no mass scatter off dust, which does have a mass, right? You would think that photons would just pass right through almost like a ghost. So how is this possible? So we're going to get into that. Okay, well, this is also about why are clouds white. Okay, so essentially, the quick answer is that blue is being scattered during the noonday sun, and that almost all other colors are getting through to your eyes. And we're going to get into the mechanics of that. But also, this is the same question as why are clouds white? And clouds are white basically because they're scattering out all of the other wavelengths, all wavelengths. They're higher up, so they scatter all of the wavelengths out, right? So that's why they appear white. But to review, we have to know what color is again. And so we've got the wavelengths of color here for the vacuum wavelengths, right? So red, we have to make a note that red is 650 nanometers, right? I'm going to write that down right now just to remind me, because we're going to be comparing a lot of red to blue, which is 450 nanometers. And just a nice midpoint, I'm going to just keep green there too. I'm going to write that down. Green is 550 nanometers. But if you remember, the wavelengths go from Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, right? So basically from 700 nanometers to 400 nanometers is what the wavelengths of light that we actually see. And again, these are the vacuum wavelengths, okay? So what is scattering, and how does light, which is a massless particle, massless chargeless particle, which is the kinetic energy of all particles, actually get bounced out, right? You would think it would get absorbed or something like that. So what's happening is this, and I'm going to mark up this document so I can make some notes as I talk to you. I'm going to make some notes in black. All right. So let's say you have a red, actually I'm going to make notes in red. You have a red beam of light, and red is this big wavelength, right? And that red is 650 nanometers. And what that means is from here to here, a wavelength is from peak to peak, okay? And I think we said it was 650 nanometers, which is 650 times 10 to the negative 9th meters. So really small, right? So this is the wavelength for red. Well, what happens is this wavelength, how it will scatter is that if you come up across a particle that is greater than the size of the wavelength, what'll happen, and I'll try to make a dust particle, right? So here's a dust particle, and it's bigger than this wavelength. And remember that red is traveling, it'll be traveling along the crest of the wavelength. So the wave is not moving like this, it's actually moving straight. So this wave is actually moving along a straight line. Well, if this particle here is greater than the wavelength, so this is the size of the particle, or height of the particle, if you will. So the height of that particle, if that height of that particle is greater than the wavelength of red, is greater than the red wavelength, then the red wave will actually hit this and then bounce back out and get scattered. And travel off of it. So that it'll scatter. If it's less than the wavelength, okay, so this is where scattering actually happens. So if the size of the dust particle is greater than the red's wavelength, it'll scatter. But if the height of the dust particle is less than the wavelength of red, then it'll pass through. And I've heard some analogies that, okay, so if you have a particle like this big and the wave kind of passes over it like that, it passes around it, really. I don't like that, because waves propagate along a straight line, as we've seen, which is why we can actually represent waves as a ray diagram, right? But it's not really doing that. Really what's happening is it's basically the size. And how wavelength is related to the size of a particle here is really kind of an interesting thing. And it gets into quantum mechanics, and you'll get into that in Physics 241. But suffice it to say, if the wavelength of red is less than the wavelength of the dust particle, or less than the size of the dust particle, and it's the overall average size, right? And we're talking about the diameter, really, the diameter here, which is, and I should represent that more as 2r rather than the height. Come on. This is going to be 2r, which is the diameter. The 2r, the diameter of the dust particle, right? It's the overall average size of it, cross length size of it. So if the diameter of the dust particle is less than red, the red wavelength will pass through. Otherwise, it'll scatter. Okay? So that's how light actually will scatter off of something. If it's basically this rule, right? If the size of the dust particle, or the diameter of the dust particle, is greater than the wavelength of red, okay, then it will actually scatter red back out into the sky. And so that's why you see sunsets that are red, right? Because some of red is getting through, right? So if you see a red sun, that means you are seeing red getting through, right? But you'll also notice that the sky is going to be kind of a combination of red. It's also going to be a combination of yellow. So there'll be, and I'm representing yellow in the sky. So the sky will have some red to it. That means some red is getting scattered, right? If the sky is red, then some of that is being scattered out, right? So basically the color of the sky the overall color of the sky is the scattered color. So the color of sky is what is being scattered. Is the scattered wavelength, right? But the sun, the color of the sun is what is getting through. So that means this. Blue is 450 nanometers, right? So blue is a really small color. So blue is 450 nanometers, right? So blue is a really small color. It's a really small wavelength, right? So it doesn't take much, right, to scatter blue back out. So even the smallest of dust particles and actually a lot of ice particles are bigger than the size of blue. So if you see the sky as blue, that means what is being scattered the most is that wavelength, which is blue. That means blue is bouncing off of that, whatever wavelength the blue is, it is smaller than the average size of the particles that are in the sky that point in time, right? So that's why you see blue being scattered the most, right? It's the smallest of all the wavelengths. The next wavelength that is able to get through, but probably then gets scattered, the further gets a little bit further, is green, right? So green will get through. It's a little bit of a bigger wavelength. It's 550 nanometers, and then finally red is 650 nanometers, right? And so it's much bigger than blue. So if we look at what's going on, it's also probability too. So if you have a light ray going all the way through this huge distance from here to here, so if you have the sun right over here, and it's got to go through this much atmosphere, right? The chances that different colors are getting through is pretty slim, right? So blue will get will get scattered first, right? So blue will get through a little bit and then get scattered back out, right? Green is going to get through a little bit, further and then get scattered back out, right? And then, you might get pink, which might be close to red, right? So pink is getting through, and it gets a little bit further, but then it finally gets scattered out. So finally, just by probability, red, being the biggest wavelength, is avoiding or is avoiding most of the little particles that are scattering back out the other colors. Okay, so it finally, just by probability, there's all these particles lined up, and so blue is going to get scattered, is actually got the highest probability of being scattered back out, right? So when it's at sunset or sunrise, and you have the sun over here, letting off all those colors, right? It's a white light, so it's letting off all the colors of the rainbow. It's just by probability going through this much atmosphere that red gets through, and that's why you see a red sun. You know, but you also see a lot of other colors in the sky at sunset, right? But when the sun is overhead, right here, well, it's only got to go through this much atmosphere, a much smaller amount of atmosphere. So when you see the sun overhead, you see blue a lot of blue is probably going to make it to your eye, right? Blue went this far. I'm going to try to be consistent with my drawing. Blue went that far, which is the same distance. Okay, but then it finally hits a particle of light, a dust particle or ice particle, and then it bounces back out, right? Green makes it all the way through, right? So if you're standing right here, green is going to go the entire distance and then get into your eyes. And then you've got yellow. Yellow's going to make it through, and so on and so forth. But the point is, the reason why the sun appears white when it's overhead is because most other colors are making it through, because it's not going through as much atmosphere, right? And just by probability, most of the colors, and even some colors of blue, which are like baby blue, for example, are going to make it through. So maybe the sun isn't perfectly white, but it's pretty close to white. It may be a little shifted towards red because a lot of blue is being scattered out first, right? Violet is being scattered out first, and then blue too. So it's a probability thing. When the further the light has to travel in our atmosphere, like at sunset and sunrise, when the sun is low on the horizon, well, it's got to go through a whole lot of atmosphere. So by probability, those particles are going to those light rays, those blue, green, and pink light rays are going to just eventually hit a dust particle, and it's going to be scattered out, right? Scattering would not occur if we didn't have any dust particles or any particles of ice or anything like that, right? So that's kind of what's happening. It's what's really happening on the atomic level is a light ray is actually hitting an atom, right? And it's being absorbed by that atom at certain wavelengths, and then it's either being absorbed, and then it'll be absorbed by that atom at that wavelength, right? If the size of this atom is greater than this, and what happens is that light ray will hit that atom, it'll absorb it, and it'll actually make the electron start to spin or move faster around that particle, that atom. So really that's what's happening. But also you could consider it actually as a dust particle too, as a huge particle. And again, that's basically the rule. So all these dust particles are absorbing light, and then emitting that light out back into the atmosphere, right? Some of that energy of that light is going to go into speeding up those electrons, but most of it is going to be re-emitted into the atmosphere at different angles, right? So the more atmosphere that that sun has to go through, the less probability that the less chance that all of these other colors get through that are smaller wavelengths. Red, being a larger wavelength, is going to get all the way through to your eyes. some of those reds are going to be scattered, right? It is a numbers game. It's just a probability thing. So that's why you see a red sunset too with a red sun. So some of that red light is being scattered out and creating a red sky. But the sun is red or maroon, darker red. So that's why that most of that color is getting into your eyes. So that's why that's how scattering actually happens, right? So when the sun is low on the horizon, right here, it's got to go through all of this atmosphere. But when the sun is directly overhead, and this is set to baby blue, when the sun is directly over your head, like right here, for example, then it's only got to go through that much atmosphere, versus right here, when the sun is low on the horizon, it's got to go through this whole amount of atmosphere, and just there's dust all over the place in here. So the chances that it's going to hit, that light is going to hit something is very high. Here is very low. So that's how scattering is working. Just to let you know, the composition of the Earth's atmosphere is mostly nitrogen. Okay, it's got oxygen, but it's mostly nitrogen. It's got oxygen and argon, and the amount of water vapor in the atmosphere is varies, right? During the dry summer months, and actually the dry winter months, there's not a lot of water vapor in the atmosphere, right? But when monsoons come, well, this is going to actually increase probably, and that's what humidity level really is. It's describing the amount of water vapor that's in the atmosphere. And there's a lot of other stuff too. The rest of the atmosphere has got a lot of dust, pollen, and pollutants and things like that. Dust and pollen and pollutants. The other thing that we kind of mentioned in the last chapter is that when light comes in, and I'm going to try to do my best to, we had a tank of water, right? A tank of water. And I shouldn't fill it in. And you have a light ray coming in. And this is kind of like, it's unpolarized light, so it's got all directions. The X, Y, and Z. Well, when the light enters and refracts into our water tank, right? So here's our water tank, right? That light ray is going to refract in. What happens is this unpolarized light, and I'm drawing 3 axes, is actually going to get polarized when it enters here, and when it reflects back out, it's actually, and part of that light when it hits the water, and this is going to be a vacuum, VACCUUM, is going to also be polarized along a different direction. So light coming in is going to get polarized in our atmosphere, right? And what we find out is that light, when it hits our atmosphere, is actually going to get polarized along the Z direction. And when it bounces back out, it's going to get polarized along the X direction. Right? And that's at that Brewster's angle, right? That Brewster's angle. Well, the light rays that are refracting into our atmosphere from the sun, and sunlight is unpolarized, are going to get polarized along the Z direction, okay? And again, so that it's you have a particle that is really big like this, which looks enormous. This is not to scale, but if it's bigger than this polarized wavelength, right? Well, then that light ray is gonna so if you have a wave, sorry, I kind of drew this. The wave would be is polarized. It's moving. Right, I'm trying to draw a z direction here. So here's the wavelength right there. So again, that wavelength, if you had a slit, right, and you had light coming through along in all directions, along in the x, y, and z directions, if you had a slit right here, if you had a piece of paper with a slit in that only allowed light to come in through the z directions, well, that is what would be passing through. Only the z direction part of the light. Well, that's kind of what our atmosphere is doing. It's kind of acting like almost like a filter that's only allowing the z direction light through. And so that's what's kind of happening too. So it's a combination of that polarization, but also the scattering that's actually contributing to more of those wavelengths being scattered back out. So that brings us to dispersion. Dispersion is not like a bad thing in physics when you cast dispersions on someone. I don't know, a big silly, but what dispersion is this. If you have white light that is refracting into any medium that's denser than that, at some point that white light is going to start being separated into its other colors, right? So if you have white light hitting, going from a vacuum, or white light in air hitting a denser medium like water or glass, well, that white light is going to begin to separate when it starts to refract into that substance at its different wavelengths, okay? And so that dispersion is when white light is refracting and being separated into its separate wavelengths. Essentially, that's the definition right there. So what is happening is that blue, which is a lower wavelength, is going to actually be bending more, which means it's slowing down more. Since we're talking about this angle right here, you have blue, which is a lower wavelength, is going to be bending more. Remember, again, frequency isn't changing, that it's still going to be blue when it goes through, but that wavelength is going to be changing, right? So if you have blue, which is a lower wavelength, essentially when it hits, so frequency isn't changing, but if you have a lower wavelength, it's going to be slowing down more when it hits a new medium, right? And if it slows down more, well, that means it's going to be refracting or bending more, okay? So red is going to be bending less than blue because red is a larger wavelength, and it's a direct proportion, right? Again, frequency is a constant, but red has a larger wavelength than blue, so it's going to be traveling at a faster speed during in that medium. So this is only, now speeds only vary when when white light hits a medium. In outer space, all of those colors are traveling at the same speed. Okay? So that kind of makes sense a little bit, hopefully. In outer space, the speed of light is c, which means wavelength is a constant and frequency is a constant. Okay? If this is a constant and frequency is always a constant, then wavelength has to be a constant too. But when it hits an atmosphere or hits a medium, well, now you have frequency is still going to be a constant, but now wavelength is going to be changing, because we learned that when we were talking about refraction, and that means the velocity of that wavelength is going to be changing too. But in the vacuum of space, well, now everything is constant, right? So again, blue is being slowed down more, so it's going to start bending more when it hits that new medium. Okay. Again, this is Snell's law, and just to confirm this, we've taken some data here, and you could do this in the light lab, and I'll show it to you in a second. So if I go to more tools on that that light lab, that link to the light lab, and I put it there in the system. So if I send this, I'm going to shoot a light ray through, and there's a little speedometer on this. If you look at this, it shows the speed of red light to be 0.67, right? But if I move this to blue, you're going to notice that it actually does change. So it's going to change the angle slightly that it's bending at, and let's see if I could put on the angles. So if I move this light ray to blue, so at red, and I'm going to put it at the darkest red possible, it shows it's traveling at 0.67 C, and it's bending at, it's refracting, or it's refracting at 31 degrees. But if I turn it to the deepest violet, now it's refracting at a lower angle, and it's traveling at 0.66 times the speed of light. That's what that C represents, right? And it gets even worse if I even make a material that is really has a high index of refraction, 1.622, and I'm actually going to make this, actually, no, air is the lowest it could be. So notice that in this, I don't even know what this is, but it's a really dense index of refraction, 1.622, so it's probably a plastic of some type. It's the angle of the blue, or actually violet, is 28.4 degrees, and it's traveling only 62% of the speed of light. Well, if I move this to red, you could actually see that bending. It's actually not bending as much. So now it's 28.8 versus, actually 28.9 versus 28.4. So it's actually 0.5 degrees less bent, and it's traveling 1% faster than the speed of violet, right? And 1% of 3.0 times 10 to the 8th is actually a really huge number, right? That's a really huge number. 1% of 1 is only, 1% of $1 is 10 cents. But you're talking about 1% of 1 times 10 to the 8th dollars, right? So that's, what is that? 10 million, right? That would be $10 million. Well, actually, that'll be $1 million. So that's a huge number. So that's what this little thing is about right here, and I put the link to the light right there. And again, we chose that far right link, which was more tools. But you could see that a lot of, in diamonds, this would be a much larger difference in the speed of light, right? The red to blue difference is as much as 2%. So This is not a small thing, especially if you're taking data from a star that is on the other side of the galaxy, right? It's a huge distance it's got to travel, and so just a little deviation is going to matter a lot in taking data in our atmosphere, right? So the strange thing about dispersion, which is the separation of white light when it refracts into a medium, is that it's actually the cause of what is a rainbow, right? So if you have white light coming in, when you have white light coming in and it hits a water molecule, that white light is going to now begin to separate, right? Red is going to bend less than blue. I'm going to mark this up. So red is going to bend less than blue. Okay, and I'm going to draw the normal on this. So I'm drawing the normal. Notice that the red wavelength is not as refracted as the blue wavelength. If I zoom in on that, it's kind of hard to see. So blue is a lower wavelength than red, therefore red is not bending as much. But here's what's really interesting. So the white light is coming in. You're standing over here. And white light is going to be coming in, and this is a huge water molecule. It's not to scale. Anyways, so the white light is coming in. It's going to be refracting and dispersing the wavelengths into their separated wavelengths. And the cool thing is that total internal reflection happens, and a little bit of that red is going to escape, right? A little bit of that red is going to be escaping, not much, and a little bit of blue is going to be escaping as well. Red is going to be escaping too. So a little bit of that light is going to escape, but most of it is going to get reflected back into off the surface and get reflected back into the water droplets. And then the cool thing is now it's when it hits the air again, it's going from water to air. Now that those wavelengths that have been separating for a long period of time are now going to be very separated when they come out. So much so that violet is now going to be seen at an angle of 40 degrees, and red is going to be seen as an angle of 42. And what I'm meaning to say is this: when you'll see the violet colors or blue colors on the inside of the rainbow, of the primary rainbow, that is. And then you see red on the outside because red is bending less. It's refracting less, right? So red is going to always be on the outside of the primary rainbow, right? And blue is going to be inside on the primary rainbow because it's refracting more. It's bending more because it's slowing down more when it hits this bead of water, okay? Well, this is just one little bit of water. Well, when you have thousands of droplets of water from rain happening, well, all of them are dispersing that white light into their separated wavelengths, and so that's why you see like a rainbow. That's why you see a cool rainbow. You just don't see a couple rays. You see the whole thing. And here's the interesting fact too: in order for you to see a rainbow, the sun has to be behind you, right? The sun has to be here behind you. And if you ever see it raining and it's not raining on you, it's raining over here further away from you and it's at sunset or sunrise, make sure you turn your back to the sun and then look at the rain, because if you do that and the sun is low enough in the sky, it's got to be directly behind you too. So I'm going to actually draw the sun directly behind you. It's got to be directly behind you, and you will see a rainbow. You'll see a rainbow right here. The cool thing is too, is your shadow should be at the center of the rainbow. So your shadow should be elongated right here, right in front of you. And your shadow will point towards the rainbow. Okay? So dispersion is happening. So this is what a primary rainbow is, right? It happens because there's a refraction, and then the white light is being dispersed, and then you have one reflection off the back of the light, raindrop, and then it keeps refracting, and then it refracts back out. And now, since it had to travel this huge path length, now the light rays are really separated a long distance, right? And for you to see that, you've got to have the sun directly behind you, not up above you. Here you won't see the rainbow. Your shadow basically should be cast in the center of the of this. I'm going to remove that. Your shadow should actually be cast along this entire surface. You know, because the sun is really big. So, anyways, my point is, you should see the whole. You should see half the rainbow. Well, why don't you see a full rainbow? Well, the horizon is cutting off the lower half of the rainbow, right? If you were above, like flying in the air, and it was raining below you, well, you would see a full rainbow below you, and you would see your shadow right at the center of the rainbow, right? And you're flying above here, and you should see the rainbow. I'm going to try to do my best to draw it. So you should see red out here, and then you should see blue at the center of that. And I'm going to try to draw blue over that. And for that, in order for that to happen, the sun needs to be directly behind you, right? And so if you're in the air looking down at a rainstorm, well, you would see this. You'd see your shadow right at the center of this, and you would see a full rainbow. The reason why the rainbow is being cut off here is you've got a horizon issue. The horizon is right there. So pretty cool. That's basically dispersion. But if you also notice, too, from this picture, you kind of see a faint hint of a secondary rainbow. And if you look closely, and I'll zoom in, notice that, again, on the primary rainbow, the red is on the outside, the blue is on the inside. But on this faint rainbow, there's just a thin little bit of red there, and blue is on the outside. So this is what is known as a secondary rainbow, right? You've got a primary, and then you've got a secondary. And the colors are reversed on the secondary, and it's dimmed. So how is that possible? Well, what's happening with this secondary rainbow, the colors are reversed. So the primary rainbow, you've got light coming in, it refracts in and disperses into its different colors. It reflects off the back of the raindrop and then refracts back out. With this dim guy, what is actually happening is the light is coming in, it's refracting and dispersing into its different colors. It is then hitting one side and then another side, and then is refracted back out. So there's two reflections here. Two reflections. And this is one reflection. And what's happening is that, so why is it dimmer too? That's another question, is, well, when the rays come in, a little bit of that light escapes, just a little bit, a small percent, right? So red and blue escape, all right, when it reflects off the back, just a little bit. It's not completely total internal reflection. It's partial internal reflection, I guess you could say. Well, what happens here is it's refracting. A little bit of that light is escaping here, and then a little bit more is escaping here. So since there's two reflections happening, each reflection, a little bit of a light escapes. A little bit of red and blue escapes there, a little bit of red and blue escapes there, and so that's why it's dimmer. And since there's two reflections, it's going to be the opposite of the primary rainbow, because it's getting shifted, its perspective is getting shifted 180 degrees, right? Reflection it shifts your perspective from looking forward to looking the opposite direction, which also the consequence of that is shifting left to right. So that's what's kind of happening with this other rainbow. And the reason why it's further out too, since it's doing two reflections, it's actually going to have a much larger angle from the incidence light ray from the white light coming in from the sun. Okay, so it's really, really cool. There's dispersion is a really neat thing. It results in very pretty things. That's also kind of what is happening. Anyways, it's also what's happening when you're flying and you're in a plane and you look down. If you've ever been on a plane and you've looked down at the clouds and you're maybe flying around noon where the sun is overhead, well, your shadow is at the center of the clouds, and you'll see like a little slight rainbow around the shadow. So you should see the shadow of the plane at the center of the rainbow, or your shadow at the center of your rainbow, right? So your little shadow should be at the center of all rainbows. Okay? So that brings us to some conceptual questions. Let's try to test what you've learned. A student wishes to photograph a whole rainbow, but her camera viewfinder does not show the entire rainbow. In order for her to photograph the entire rainbow, what should she do? Should she move closer to the rainbow? Should she move farther away from the rainbow? Or should she just go out and buy a wider angle lens? What do you think she should do? Okay? And take a moment, pause the video, think about it, and think about those angles of that the light rays were coming out. And let's see what you think. Pause the video now. Okay, we're back. So I'm going to change this black. So you know blue is going to be coming off, and I think blue is being refracted out. Well, all of that is being refracted somewhere between 40 and 42 degrees, right? So red is going to be 42.5 degrees in blue. So this is coming off at 40 and 42 from the light rays that are coming in, right? So this angle should be, and this one should be 42, and I'll just say 40 degrees. So it's ranging from 40 degrees to 42 degrees, right? Well, if you back away from that, that rainbow is just going to follow you backwards, right? Because that has to always maintain 42 degrees, right? So that 42 degrees, the white light, the incident angle coming off of that is going to be 42 degrees, correct? And that one's going to be 40 degrees. So those have to be maintained. Backing up or going forward is just going to shift the rainbow forwards or backwards, right? So moving back and forth from the rainbow, since your 42 degrees has to be maintained, the rainbow is just going to move back and forth with you, right? That's why you should never go chasing rainbows, because you'll just end up running forever. Or you'll end up running into the rain, and then the rainbow will disappear. But my point is that what you have to do is buy a wider angle lens, and that will allow you to catch that 42 degrees inside. So that's what she should do. Let's try this. When seen from an airplane, a rainbow sometimes forms a complete circle. When this happens, the plane's shadow is in the center of the rainbow, the lower part of the rainbow, the upper part of the rainbow, totally outside the rainbow, or nowhere, because there is no shadow caused by an airplane. So go ahead and pause the video and try to recall what we talked about. Pause the video now. Okay, we're back. Well, we had talked about how if you're standing right here and you see a rainbow, and you're seeing a rainbow, and it would be a half rainbow on the Earth. Red is going to be on the outside. Blue is going to be on the inside. Actually doing a pretty good job of drawing that. Oops. No, I don't want to zoom. I'm sorry. I drew a pretty good rainbow and then I messed it up. Erasing it. So here is a pretty good rainbow. Alright. And then here's the horizon. Well, we had talked about that your shadow should be at the center of this rainbow, right? And then it gets elongated from your body, right? And we also talked about how the sun has to be right behind you. Well, if this gets shifted now, now you're flying above the clouds and it's raining. The clouds are right here. If you look down, you should see the shadow of the airplane at the center of the rainbow, and you should see an entire ring of the rainbow right there. So, and you'll see a full rainbow. So that's pretty cool. So basically, in order to see a full rainbow, you just have to get above it. You just have to get above it so that again, this happens probably the best time to fly is at noon. That way you could, and you have a window seat, you could see the rainbow. Pretty neat. Okay. So there's some cool consequences of this. Since red is not bending as much as blue, well, that means if you have little laser pointers of different color and you're trying to hit fish that are a different color than your laser pointer, you might have to correct as much as half a degree or maybe even 1 or 2 degrees, right? So let's review. If you want to spear a red fish with a red laser beam, where should you aim to hit the red fish with your red laser beam? Should you aim above the sighted fish, below the sighted fish, or right at where the sighted fish is? And here's where you see the fish. So go ahead and pause the video and try answering that question. Okay, you've unpaused the video. So here's where you see the fishy, right? So the light ray from the red fish, and I'm going to try to use a red color to draw the light rays of that, is coming. So the sighted fish is the fake fishy. That's not where the real fishy is, right? So you see along a straight line right here, right? But the actual fishy, the red fishy, the actual location of the fish is down below it, right? So that light ray is going to be bending more. And I'm going to use this black to draw the normal. Okay, so the normal occurs when the light ray, so the actual fish is right here, and that means that light ray is going up from the fishy, and when it hits the interface to air, this is water, it's going to bend into your eyes, right? But we'd also learned too, if you want to grab the actual fish, you need to grab below where the fish actually is. But if you want to hit it with a laser, well, that laser beam is going to follow the same path as the red light from the fishy. So the red light from the fishy is going to be leaving and refracting out into air and bending away from the normal back into your eyes. So if you want to hit it with a red laser beam, aim at where you sighted, directly at where you sight the fish in, and that way you'll hit it. It'll just follow the same path. Why is this on here twice? Interesting. So let's move on. But this is going to be different if you're trying to hit a red fishy with a blue laser beam. So anyways, this is the answer to that last question, the red fish with the red laser beam. Okay, so I included this slide just to clear up anything that I didn't draw a very accurate drawing the last time. But now you have a blue fish that you want to hit with a red laser beam. Now where should you aim to hit a blue fishy with your red laser beam? And I should draw on here that this is the sighted fish. So let me include that in here as well. So this is where this is where you see the fishy. Now where should you aim in order to spear this fishy, not really spear, but hit the fishy with a red laser beam? Above or below or directly at where you see the blue fish? Go ahead and pause the video and let me know what you think. And we're back. Well, let's put it this way. If you shoot a red laser, and so what we had talked before about is you should shoot a red laser at a red fish. That way it'll follow the same path of light that the fish is giving out, right? The fish will have its light leave the water and bounce into your eyes and refract into your eyes. Well, you should shoot directly at where you see the sighted red fish, and that way it'll follow the same path that that red light took from the red fish. Well, that is not going to be the case here. A blue light is going to bend more than red. Okay, so I'm going to draw a blue light beam from the fishy. Okay, so this is, you're seeing the fishy right here. The fishy's light is leaving right here, and that's where you see the blue fishy. Correct? Well, the actual blue fish is going to be below. The blue light beam is going to be bending below here, and so you're going to see the blue fish somewhere right here. So here's where the actual blue fish is. Okay, so the actual blue fish is below where the sighted fish is, just like the red fish was. However, the red laser beam is, if you shoot directly along that path, what's going to happen is a red laser beam is not going to bend as much as blue. So if you shoot along that path, what's going to happen is it's going to follow a different path, and it's going to just overshoot the actual fish. So what you have to do is you have to aim below where you see the fish. And I think this is better drawn on the next slide. So in this explanation, the apparent blue fish, which is green, is going to be above where the actual fish is. So the blue guy is the actual fish. I'll make a note of that right here. So actual. actual. So the actual blue fish is right here. Well, the light is going to leave the blue fishy, and then it's going to refract away from the normal into your eyes. If you shoot directly at where you see the fishy, what's going to happen is the red is not going to bend as much as blue because it's not changing its speed as much, it's not slowing down as much, and it's going to overshoot, right? The red beam is going to end up missing the blue fishy, right? Or maybe hitting its tail. I don't know. You want to kind of nail it right in the smiley face. And what you should do is you should correct for that by aiming below where you see the blue fishy with the red laser beam. All right. Well, in summary, what we've gone through here, we've gone through light rays. We've gone through what is light and how it is a photon and a wave. But also how you could view both of those as just straight line rays. We use that to help us look at what is reflection and what is refraction. And we talked about Snell's law and how you could predict the angles at which light is going to be bending when it goes through different mediums. We talked about polarization. We did internal reflection. We talked about that critical angle. And then we talked about scattering and dispersion of light. So now in the next group, what we're going to do is go on to spherical mirrors, so not spectral plane mirrors. Okay, spectral plane mirrors are just flat mirrors. We're going to be talking about what happens, what do you do, how do you draw those rays when the mirror is actually bent or spherical-ish. And also with lenses too, how do lenses work and how do lenses focus light. And then we're going to talk about what is the eye and how do you correct vision with multiple lenses and things like that, and also what is a microscope and also what is a telescope. So please check those out after you go through this.